Welcome to the deep dive. Today we're really getting into it, looking at gravity itself.
Yeah, specifically questioning if Einstein's general relativity, our best theory of
The
gravity.
gold standard.
Exactly. If it's maybe, well, incomplete on the really grand scales.
Because general relativity works brilliantly, right? For most things.
Yeah.
Solar system, black holes.
Oh, absolutely. Its successes are huge. But when you look at whole galaxies, how they spin, or the universe's large-scale structure,
Things get a bit weird.
they do. You see galaxies spinning way too fast. The visible stars and gas, they just don't have enough mass, enough gravity to hold themselves together at those speeds according to standard physics.
Which is where the idea of dark matter comes in.
Precisely. This invisible, non-interacting stuff that supposedly provides the extra gravity needed, it's the standard explanation.
Okay, so dark matter is like the universe's missing ingredient that makes the current recipe work.
You could put it that way.
But what if the recipe itself, the physics of gravity, needs adjusting? Not missing stuff, but different rules.
That's the alternative path. And it leads us to something called modified Newtonian dynamics, or MOND.
MOND. Okay, tell us about that.
Well, MOND was proposed back in the early 80s. It suggests that gravity doesn't strictly follow Newton's law or Einstein's description. When the gravitational pull, the acceleration, becomes incredibly weak.
Weaker than usual.
Much weaker, like in the far outer regions of galaxies. MOND proposes that in those conditions, gravity is actually a bit stronger than predicted.
Ah, so you wouldn't need the extra dark matter glue because gravity itself does more heavy lifting out there.
That's the core idea. No need for vast amounts of unseen matter, just a change in the gravitational force law itself under specific conditions.
That sounds, well, pretty radical, honestly. Challenging Einstein and Newton.
It is bold, definitely, a fundamental shift.
But has MOD had an easy time getting accepted? I imagine there'd be pushback.
Oh, absolutely. It hasn't been smooth sailing. Some of the simpler initial versions of MOND ran into trouble.
Trouble like what?
Well, a big one was the observation of a neutron-star merger, GW1C0817.
Right, I remember that. Gravitational waves and light arriving almost simultaneously.
Exactly. And that observation put really tight limits on how fast gravity travels and sort of how it behaves. It basically ruled out some MOND theories that predicted gravity might propagate differently.
So some versions of MOND didn't survive that test.
Correct. The simplest modifications struggled to match those observations.
Okay, so the debate isn't settled. People are still looking for ways to tell the difference, right? Dark matter versus modified gravity.
Definitely. The search is on for new tests, new environments where we can probe gravity under the right conditions.
And what are those conditions?
Extremely low acceleration. That's where MOND's effects, if they exist, should be most obvious compared to standard gravity.
So we need a natural laboratory with incredibly weak gravity.
Precisely. And it turns out we have them. Very wide binary star systems.
Pairs of stars orbiting each other, but really, really far apart.
Extremely far apart. We're talking separations bigger than, say, 5,000 astronomical units, 5,000 times the Earth-Sun distance.
Wow, that's vast.
It is, and because they're so far apart, the gravitational pull between them is minuscule. The orbital accelerations are down around 10 to the minus 10 meters per second squared.
10 to the minus 10.
Mhm.
How does that compare to Earth's gravity?
Earth's surface gravity is about 9.8 meters per second squared, so these accelerations are roughly 10 billion times weaker.
10 billion. Okay, so these wide binaries are perfect test beds for that low acceleration regime where MOND might kick in.
Exactly. They're like super sensitive probes drifting through space.
And people have looked at these before, right?
Yeah.
Using data from the Gaia Space Telescope.
Yes, there were earlier studies using Gaia's first and second data releases, DR1 and DR2. They found some hints, maybe, of MOND-like deviations.
Hints, but nothing conclusive.
Not really definitive proof. The data was good, but maybe not quite precise enough, or the samples weren't large enough yet.
So the big push came with Gaia's data release 2, DR2, diving deeper into these wide binaries.
That's right. DR2 really opened things up. A key study was by Pitortis and Sutherland in 2019.
What do they do?
They sifted through the Gaia data, identifying something like 25,000 potential wide binary pairs relatively nearby within 200 parsecs.
Okay, a big sample.
And they focused on brighter ones for better measurements, with separations going way out, up to 40,000 astronomical units.
40,000 AU, that's huge. Almost a light year across, nearly.
It's incredible they stay bound at all.
So what happened when they compared the star's actual motions to what standard gravity predicts versus what MOND predicts?
They looked closely at the ratio of the observed velocities between the stars compared to what Newtonian gravity would expect, especially for pairs between 10,000 and 14,000 AU apart.
And the results?
Well, the simplest original MOND model, it didn't fit the data well at all.
Oh, so bad news for MOD.
Not entirely,
Huh.
because a more refined version of MOD, one that includes something called the external field effect, actually did much better.
External field
Yeah.
effect. What's that?
It's basically acknowledging that these binaries aren't totally isolated.
Mhm.
They still feel the gentle background gravity of the entire Milky Way galaxy.
So it's like context matters, even for gravity.
Precisely. And when they factored that galactic tide, if you will, into the MOND calculations, the agreement with the observed velocities improved significantly.
Okay, so MOD with this external field effect looked pretty good.
It looked better, but there was the complication.
Always a but, isn't there?
Often, they found this unexpected long tail in the velocity ratio data across all the separations they looked at,
A long tail, meaning what?
meaning there were more binary pairs with higher relative velocities than either Newtonian gravity or MOND with the external field effect could easily explain.
So even the modified MOND didn't fully capture everything.
It seemed not. This tail was a bit of a puzzle. It made it hard to say definitively, yes, this looks like MOND, or no, it's just Newton plus something else.
So what could cause that tail, that excess of high velocities?
Pitt-Tortoise and Sutherland suggested a couple of possibilities. Maybe some are just chance alignments, flybys, not true bound pairs, perhaps leftover from when they formed in star clusters.
Okay, contaminants in the sample.
Potentially. Another idea, explored by Clark later, was that some might be hidden triple systems.
A third star lurking unseen, messing up the velocity measurements.
Exactly. That could definitely complicate the picture and maybe explain some of those higher velocities.
So the long tail could be mundane astrophysics rather than new physics.
It's possible.
Yeah.
That's what made the DR2 results intriguing but not conclusive for MOND.
You mentioned another study too, Hernandez et al. Did they find something similar?
They looked at a smaller, very carefully selected sample, about 81 wide binaries. They found that below about 7,000 AU separation, things looked pretty Newtonian.
Okay, standard gravity works fine for the closer wide pairs.
But as they looked at wider pairs, beyond 7,000 AU, they started seeing deviations again. Hints that maybe Newtonian gravity wasn't the whole story out there.
So similar hints, but again, not a smoking gun for MOND.
Pretty much. Gaia DR2 was fantastic. It showed the principle of using wide binaries to test gravity works.
It proved the concept.
Yes, powerfully. But it also highlighted the challenges, cleaning the samples, understanding all the potential astrophysical effects. It didn't give us the final answer on MOND.
But Gaia is still observing,
Yeah.
still collecting data. Right?
Absolutely. And that's why there's so much anticipation for Gaia Data Release 3, DR3.
More data, better precision.
Exactly. Better measurements of star positions, motions, maybe even identifying more of those hidden triples or flybys. DR3 might have the statistical power and precision needed to really separate the signal, whether it's MOND or something else, from the noise.
So DR3 could be the moment of truth, or at least a much clearer picture.
That's the hope. It could potentially help us finally distinguish between these competing ideas.
It's fascinating.
Yeah.
But beyond testing fundamental gravity, just studying these systems,
Mhm.
these incredibly loosely bound pairs, must tell us a lot about star formation and how things evolve. Right?
Oh, absolutely. Their mere existence is interesting. How do they form so far apart? And how do they survive?
Survive. Because they seem so fragile, gravitationally speaking.
Extremely fragile. This goes way back to Victor M. Bartsumian in 1937. He realized these wide pairs are very susceptible to being slowly pulled apart.
Not by dramatic collisions, but just gradual disruption.
Yes, by the cumulative effect of countless tiny gravitational nudges from all the other stars they pass by over millions and billions of years in the galaxy, the galactic tide, distant encounters, they slowly chip away at that weak bond.
So they're destined to eventually break up.
Most likely, yes. The wider they are, the faster it happens.
What kind of timescales are we talking about?
Well, estimates suggest that for a really wide pair, say half a parsec apart that's over 100,000 AU, the breakup time might be around 100 million years.
Okay, short on cosmic scales.
Relatively, yes. A slightly less extreme wide binary, maybe 0.1 parsec separation, might last for over 1 billion years. Their orbital periods are immense, of course. To us, they barely look like they're moving relative to each other over human lifetimes.
It really puts things in perspective. These slow, delicate cosmic dances playing out over eons governed by forces
Mm,
we're still trying to pin down perfectly.
it really does.
Which kind of brings us back to the big picture, doesn't it? If even something as fundamental as gravity might behave unexpectedly in certain regimes, revealed by these incredibly faint interactions in wide binaries,
It makes you wonder.
yeah, it makes you wonder, what else about our understanding of the universe, what other basic physics might still be incomplete? What assumptions are we making that future observations, maybe even more precise than Gaia's, might overturn?
That's the perpetual quest of science, isn't it? Pushing the boundaries, refining our understanding, and always being ready for surprises from the universe. These wide binaries are just one fascinating window into those deeper questions.